Hello. It's a real pleasure and honor to be here. Thank you for all coming. So in my group, we have been using AI and machine learning for many years to understand better natural intelligence. And in this talk, I'm going to be focusing on human face processing and how we've gained greater insight by using AI. So as you might already know from your daily experience, humans are very good at face processing. For example, at a mere glance, you can assess demographic traits like gender, age, and race, as well as emotional state. Is this person looking happy or sad or angry, etc.? And social traits such as, is this person looking intelligent or kind or shy, and so on and so forth. And also recognition or similarity. Is this somebody I know? Does anybody recognize this person? Great first name, by the way. So in fact, even babies are real face experts. When babies are only 7 months old, they already show looking preference for more trustworthy faces as judged by adults. And in fact, I don't know if this is depressing or impressive, but two-day-old infants prefer to look at more attractive faces. And even newborns who are less than 60 minutes old already turn to more face-like stimuli. So for example, they prefer to look at this schematic-looking face stimulus compared to a scrambled version or blank. And literally, they just come out of the womb. So it's not true, however, that humans always excel at complex vision tasks. For example, if you look at tumor detection, even back in 2017, which is dark ages, back in the dark age in terms of machine learning and AI development, deep neural networks already were shown to greatly outperform well-trained human pathologists. However, we didn't evolve to detect tumors in microscope images. We evolved to process faces because they're critical for survival and mate selection. You need to know you need to know which are your friends and your enemies so that you can form social relationships and survive at group level. And you also need to be able to reproduce, and for that, to find a partner. And face-related information is very important for that. And as such, we can see face processing as a prime case study of sort of epitome, or one of which, of human intelligence. And thus, we have a virtuous cycle. So we can use AI, artificial intelligence algorithm, to better understand how humans represent and process faces. But we can also use the scientific insights we gain to return it back to artificial intelligence and perhaps improve the performance or capabilities of AI systems. So the model that we primarily used in my group for analyzing face representation or modeling face representation and processing in humans is the active appearance model, which is not a deep neural network model, or at least not only, but has proven to be most successful in capturing human representation and behavior. So remember those face-like images a newborn baby's leg? Well, it turned out that computer vision scientists already developed this algorithm, this active appearance model, which I will abbreviate as AAM, back in 1998, in the late 90s. And the algorithm basically looks like this. It takes a face image, and so back in the days, they had to use poor undergrads to annotate all the landmarks, but these days we can use deep neural networks to do this. So there's a consistent way for annotating the landmarks on all the face images in a large data set. And the XY coordinates of these landmarks compose the shape features. And then we warp each face image to the standardized landmark locations. And the pixel values are what we call texture features. So then we decompose each face image into shape and texture features. And just in the last few years, this model has been applied to show that it captures well what face-sensitive neurons in the primate brain, in particular in monkeys, are selected for. And we have also applied to a number of different applications in human face processing to show it's a very good model. And it's probably no surprise because, as you can see, what babies care about is the schematic type of diagram or face-like image where you have these eyes and eyebrows and nose and mouth and so on and so forth. And that is what the landmarking algorithm is also trying to capture. And then it fills in the details with all the texture information as well. So the first phenomenon I'm going to try to explain to you guys that we have been able to understand better with these computer vision methods is beauty and averageness effect. So this is something that's actually been known for almost a century and a half by psychologists, that when you blend two faces together, people tend to find the blended face more attractive. So here an example is 4 individual faces that have been blended into 2 face blends and then 4 face blends. And there have been qualitative hypotheses proposed in the past, such as symmetry or smoothness, that have tried to explain this phenomenon. But in fact, humans also show, including babies, show a preference for more average-looking birds, cats, fish, cars, and even synthetic dot patterns, implying this is a general cognitive mechanism not specific for mate selection or reproduction. And now I want to, so the first puzzle we're going to try to understand scientifically is why. Why do people prefer more average-looking faces? But before I tell you the whole story, I'll give you a little bit of background. So as you know, that so modern AI has been very powerful. It does lots of amazing things. But one catch is that it's very energy intense, right? So this is a figure from The Economist in 2020, so it's already a little outdated. But what it's showing is that the amount of energy that it takes to train deep neural networks or AI system has been increasing exponentially. And it's been increasing exponentially at a much higher exponential rate ever since the dawn of the modern era, which is when deep neural networks became possible of being trained. It's on a log scale in the y-axis, which is why it looks linear, but it's increasing exponentially. On the other hand, the brain is highly efficient. We can't afford to have very inefficient processing in the brain. And so Horace Barlow, who was one of the pioneer neuroscientists and psychologists and vision scientists from Britain, proposed the efficient coding hypothesis back in 1961. And the idea being the brain doesn't have arbitrary representations, but has a representation that's highly efficient. So what does efficiency mean? Claude Shannon in 1948 came up with the source coding theorem, among other mathematical results he proved in relation to information theory. And one of the theorems, which is this source coding theorem, he proved, is that the maximally efficient code must incur cost that is for a data item x, incur cost of negative log probability of x. That P of x is the probability you're going to encounter this data in all the possible data you're going to encounter in the world. So what that means is that the more common data should be assigned less costly code in terms of bits. This log-based 2. So for example, if you're probably encountering a data point is high, then log P of x is also larger, and then cost of x should be smaller. And so one example for getting intuition for this is Morse code. If you look at Morse code, so here's the diagram for Morse code, you see that the more commonly used letters, such as A and E and I and S and T, are some very short representations, very short code. So a dot is 1 unit, a dash is 3 units, and then there's also a space. Whereas very infrequently used letters such as Y and J and Q are some much longer codes. And this kind of assignment is highly efficient overall because on average, you're much more likely to encounter the frequent letters rather than the infrequent letters. So the average code length would be shorter if you assign code cost this way, right? So we don't know exactly how the brain represents data in the brain, but to be efficient, it must be such that the energetic cost should be smallest for the most frequently encountered observations. So if we imagine the distribution of faces in the brain and over some feature space is something like bell-shaped or Gaussian mathematically, then what the source coding theorem said is that the more typical face, which maybe lives in the middle of the Gaussian, which is very commonly or very likely to be encountered, should incur a low cost. So if you look at the brain, it should look something like this. Whereas in the atypical face, which lives at the edge of this distribution, should incur a high cost. And that's how, overall, as you walk around, look at different faces, you can be maximally efficient in coding the stimuli that the brain encounters. So what we're proposing is that the brain must have some internal sense of coding costs in being able to become so efficient at representing the internal environment. And this coding cost is experienced as disliking. So it's this subjective sense of fatigue that makes you feel like, I've had enough. And this disliking is the signal involves your brain to use neuroplasticity to adapt to the statistical environment, both through development and also during adulthood when you say immigrate to a different country where the faces are very different. Of course, this doesn't only apply to faces. It applies to all kinds of stimulating environment. Whoops, sorry. And another thing to note for you AI aficionados is that this log probability of X term, also known as log likelihood, is also the cross-entropy term that's commonly used in machine learning algorithms and in particular training neural networks. So the neural networks are trying to maximize basically the likelihood of encoding the stimuli in the training data set. Now back to this beauty and averageness effect, this effect that when you blend faces, they become more attractive. So on average, when you blend a face 1 and face 2, on average, the blended face will be more likely to live in the middle and therefore have a higher log likelihood. And therefore, in your efficient brain, you should encode lower cost. And that makes you think, I like this face. And, OK, so so the first thing we checked is that the distribution of faces in the face space, indeed, in the AAM face space, is indeed multivariate Gaussian, this bell-shaped thing. And it really is. So when you look at different dimensions, it looks more or less Gaussian. There are a couple of exceptions, which I'll come to in a second. And because log likelihood of a Gaussian distribution is just the quadratic form, it means that it's just a nice quadratic function. And then what we did was we collected human judgment of how attractive, trustworthy, dominant, and valence. Valence means how positive does it look. Does it look happy or friendly, positive valence? People's judgment strongly linearly correlated with the log likelihood of that face image in this population distribution. We did not fit any parameters at all. We simply took a large data set of face images, looked at the projection of faces in this AAM feature space, fit a multivariate Gaussian, compute the log likelihood of this each face, and then we can see there's a strong linear correlation with all these subjective judgments. So that is not to say that typicality is the only thing that matters when it comes to a social judgment for faces in humans. In fact, there is at least one additional linear component as well, in addition to this shared quadratic component. But what we do see is that this log likelihood typicality measure drives many types of social liking, such that it has the largest contribution to attractiveness, followed by trustworthiness, followed by dominance, followed by valence. Valence is the smallest. So this is probably why people notice beauty and averageness first. I mean, psychologists notice beauty and averageness first before they notice trustworthiness and averageness. And in fact, dominance and averageness has never been reported until our study, nor valence. And it's perhaps not surprising that this subjective liking should not be confined to only attractiveness, because it's just a subjective feeling good factor. So it also influences other types of social judgments. And there's also neural support for this. More atypical faces evoke greater neural activation in the face processing areas in the brain. For example, amygdala and the fusiform face area. And if you use EEG, which is another method to measure brain activity, you see that face-specific component of the EEG signal is also larger for more atypical and unattractive faces, as well as people's reaction time to say that's even a human face. And we also analyzed neural data from the monkey brain, where there are face-selective neurons in the monkey brain that respond to faces. And we find the mean firing rate, so the average neural activity of these neurons, are also greater in proportion to negative log likelihood. So as I said, there's also linear component, because what we perceive as more attractive or trustworthy or threatening are not actually exactly the same. They just share this common quadratic component, but each one also has a linear component. So it might look something like this if you're looking top down, right? So you have this quadratic factor, but then you have linear factor that's specific to each trait. And this, what we find, is the best model for human perception of faces. And what I'm showing here are actually the models generate the synthetic faces to show you what the attractive linear axis looks like, what the trustworthy linear axis looks like, and what the threatening axis looks like. So a more interesting scenario is when you have a multimodal distribution. If it's not a Gaussian, but actually is a mixture of two components, then what's average is not what's typical. What's average here is then in the middle, and it's neither typical for one mode nor the other mode. And so then we can really unconfound the origin of this attractiveness or building up attractiveness phenomenon and trying to figure out whether it's really about being average or typical in a statistical sense. And actually, there is a fairly robust amount of experimental data in the psychology literature showing that, relates to this phenomenon called ugliness in averageness. Not my naming, it's a nomenclature from the psychology literature. So what happens is they blend two faces, but except the faces come from either two different races or two different genders. So here's a multi-race blend, this is a multi-gender blend. And so if you just show the middle face to people, observers perceive them as more attractive than either of the parent faces, just like normal blended faces. But if you first ask people to do a categorization task, for example, race categorization in this scenario, then people find the blended face to be much less attractive than either of the parent faces. And same thing for gender categorization for the gender blend faces. So our hypothesis is that task-dependent attentional modulation of the face representation in the brain is modified in a task-dependent way such that you throw away or suppress all the feature dimensions not relevant for that particular categorization task, because certain face features are important for gender classification, but others are not. In that subspace, the distribution looks bimodal. It better be, otherwise you cannot classify male from female. And so in that space, in this bimodal space, the blended face is right on the boundary, and that's why it's not very it doesn't have high typicality, and people perceive it as less attractive. So remember I told you that in this big space containing all the face features, it more or less looks like a multivariate Gaussian. But if you project down to a single dimension that best discriminates gender or race using linear discriminant analysis, one of these machine learning tools, then you see the distribution indeed bimodal in the face space. So this is from actual data. And then if we simply predict, now we fit a bimodal distribution, just a mixture of two Gaussians, we can now, so this is actual, this is data from subjects judging the attractiveness of faces after doing gender categorization. And what's on the x-axis is how much percent, what's the percent of female versus male faces in the blended face. And then you see this ugliness in averageness effect, UIA effect, which we can reproduce in the gender discriminant subspace. But in the full space, you will still have the BIA effect. And we can actually do this on an individual face basis. Again, there's no free parameter at all in the model. We simply take the face distribution over the entire feature space. We throw away all the features that don't help with gender categorizations, only focus on those that do. And then we read out, and so we have a bimodal distribution, read out the log likelihood for each face, and now we can predict how people perceive attractiveness in that subspace. And we've also done the same for race blends and can get the same effect as what's observed in human data. So in the last part of my talk, I'm going to talk a little bit about another application of this face model, which has to do with gender differences in politics. So as we all know, there are gender biases in politics and workplace in general. In particular, I got very interested in this problem when in 2016, Hillary Clinton was running against Donald Trump for presidential election. And in surveys across potential voters, she was said to be viewed as untrustworthy. And voters said they don't trust her, even though they couldn't say exactly why. So rather, even if they were Democrats, the most negative perception of her was that she was untrustworthy. And I thought, well, can this in part be due to face-based social perception? But that would be consistent with people not being able to say why, but everybody being so sure that she's untrustworthy. And so the first thing we did was to look at human judgments of trustworthiness and dominance. So T stands for trustworthiness, and D stands for dominance. And you see that for female faces, human judgment of the two are highly anti-correlated, while for male faces, there's a very small correlation that's barely significant. And what that means is that fewer females than males would be judged as both trustworthy and dominant. And that would be a major disadvantage for female candidates if both of these qualities are desired in, say, elections. And that's because when it's anti-correlated, you're not going to find very many data points or faces that fall into this region where it's high both on the dominance dimension and high on the dominance dimension and high on the trustworthiness dimension, right? But for male faces, there would be more faces in that region because it looks more like a circular distribution. Okay, and the next thing we verified is indeed when we ask subjects to give relative judgment of pairs of females faces, whether which one they prefer more as an election candidate, we found that indeed the model estimated trustworthiness ratings and model estimated dominance ratings were both correlated with how likely people were saying that they were preferred that female candidate. Meaning that both traits are perceived traits are indeed advantages in elections, and this anti-correlation would uniquely disadvantage female candidates. And we also found the same for job applications. So we asked subjects, if this is the person you're interviewing for a job, how likely you're going to choose this person over that person. And separately, we have a model that predicts trustworthiness and dominance of each face image. And we found that indeed the trustworthiness and dominance ratings of each face also positively predict how likely people were to prefer a candidate for a job application. So where does this anti-correlation come from in female? Oh, finally, I want to say that so a deep question that some of you may be wondering is, where does this difference between male and female faces come from? Why is this anti-correlation only for female faces, strong anti-correlation only for female faces and not for male faces? Is it that women are just unlucky? We happen to have face that either look trustworthy or dominant, but not both, and male faces tend to have, show both traits? Or is it because people actually use different criteria to judge female and male faces? We found it is the latter, because if you train a trustworthiness or dominance prediction model on only the male faces applied to female faces, there's absolutely no anti-correlation. And if you train a model on female faces and to predict male faces, then you see extremely strong anti-correlation. So that anti-correlation really comes from how people judge female faces differently for these social traits than male faces. So then the next thing we did was to look at in the face feature space, where does this anti-correlation actually come from for female faces compared to male faces? So in the first row is female dominance. So the model says, OK, if you go in this direction, it looks more dominant. If you go in that direction, it looks less dominant. The second row, going to the right, is more trustworthy female faces. And the third row is male dominance. The fourth row is male trustworthiness. At first glance, it looks like, well, actually, male and female trustworthiness and dominance judgment seems to be very similar to each other. If you look at dominance, for example, this more dominant the female dominant-looking face is not that different from the dominant male-looking face. And if you look at the trustworthy-looking female face, it's also not so different from trustworthy-looking male face. However, if you look more closely, you see that the female what human subjects perceive as more trustworthy in female faces is not highly, but significantly correlated with femininity and age, the perceived femininity and age. And then we looked at data to see that indeed the perceived age and femininity of the face drive how people perceive how trustworthy a female face looks. So for example, if you go to the right, you might perceive this face over here as both younger and also more feminine. Whereas if you go to the left for dominance for female faces, you also perceive this as younger and more feminine. And because they're going opposite directions, that's where the anti-correlation primarily comes from. For male faces, it's a slightly different story. For dominance, when you go to the left, it's also less masculine looking and younger looking. However, in the bottom row, there is no correlation with either gender or with perceived masculinity or age. In other words, the difference between how people perceive female and male faces and judge their social trait is much more gendered for female faces, especially in trustworthiness. To summarize, I think that's all the time I have. There are many ways how artificial intelligence and natural intelligence can help each other. So in this particular example that I'm showing you applied to face processing, we've learned something about by using AI algorithms, we can better understand human face processing. And we have learned things like a form of intrinsic motivation, like typicality of a face. We learned something about top-down attention, which features are actually attended to and not attended to when you do different tasks, like race versus gender categorization, and also the provenance of some of these human biases and where they come from, such as gender differences. In the other direction, maybe we can also inform AI algorithms, such as how the brain managed to be efficient and adapt to changes in environmental statistics, as well as become more aware of the bias in human judgments and therefore make more fair AI systems. So finally, I just want to acknowledge the members of my lab, some data that was shared by Darmstadt and Winfried Freiwald, as well as open access data and code, and finally, funding. And I'll take any questions if there are any. Thank you.
So thanks a lot for the interesting talk on how we process faces. I see there's already some first questions over there. Please go ahead.
It's always great to hear a scientist talk about beauty, right? One of the things about faces is that you can do something about the perceived beauty of a face, right? And many people spend a lot of money on it, but it's sort of maybe a slightly unnatural thing, right? Whereas the domain where beauty is the objective is, of course, the arts. So I'm wondering whether the hypotheses you discussed here, in your opinion and experience, would also apply to, let's say, visual arts or music, where I find it much more difficult to believe that coding efficiency is a major driving factor. Do you have any results on this or any insights into it?
Yeah, so we haven't looked at arts per se, but that's a good question. I've thought about it. I mean, firstly, I want to say that even attractiveness in faces is not a pure quadratic function, right? So there's also a very strong linear component. Actually, it's more important than the quadratic component. So what you perceive as beautiful for either art or music may depend on that too. And the other thing is that it may depend on your feature representation, right? So what an amateur perceives as more typical could be very different than what an expert perceives as typical, because the way you represent art or the features you use to represent art, represent music might be quite different. So this preference for more novel kinds or different kinds of art may be because it's probably due to the fact that not only you view more art, but that your internal representation has been shaped by the art pieces you viewed, right? And so maybe it actually looks more like it's very multimodal in this high-dimensional space. And when you create new art, it's possible that you're trying to connect different kinds of modes to come up with a new type of art. I mean, there's very much we don't know about the art space. I think it's very interesting, yeah.
Thank you, Angela. Very interesting talk. You went into several directions, but one of the first thing you mentioned, I think the picture is still there, about the children, infants who are liking smooth, symmetric faces. And you are trying to give one explanation from the efficient coding, but if I'm trying to think of the evolutionary perspective, what really a children is, or an infant is trying to do is basically cling to someone so that they can survive, right? And if that's the functional requirement that they are trying to figure out, then smooth, symmetric probably means someone who is healthy. And that might be a evolutionary shortcut?
I mean, for babies, I don't know if that matters. It needs to be protected by its mother and not be, given up or, attacked by an enemy or a predator or something. That's the most important thing. But we have looked at smoothness and symmetry, and we found they're both subcases, special cases of typicality. The overarching theme is typicality and not symmetry or smoothness, right? Those are just special examples. So if you increase either of those, your typicality was also increasing in the face. And how a baby can assess typicality, it doesn't have this internal probabilistic distribution and blah, blah, blah. It turns out that if you average just a few faces, say a handful of faces, you can already get an average face looks pretty much very close to the mean of the entire population. So if you take female white faces, for example, and take any 8 and average them, they all pretty much look exactly the same and indistinguishable. So what that means is that the baby only needs to view like a handful of faces before it already has a pretty good sense what a typical face is. And hopefully that answers your question, like mechanistically how this can be done.
All right.
So thanks a lot for the questions, and let's thank our speaker, Angela Yu, once more. So.
Thank you very much.